this is functions of several variables optimization. Shows that the function f of x and y equals 6 plus 4x minus 3x squared plus 4y plus 2xy minus 3x through 3y squared has one critical point, and classify the critical point. What is critical point means? What is the critical point? Do you know?
Critical point, I remember from optimization. Critical point, it's whether maximum or minimum, yes?
Yes, yes. Critical point is maximum or minimum, and we can calculate or know where is maximum or minimum by making the derivative, first derivative, right?
Yes.
And classify this critical point is maximum or minimum. So we will calculate df dx. So we'll take the derivative with respect to x. What is the derivative with respect to x?
Derivative with respect to x? It would be 4 minus 6x plus 4y.
No, 4y is constant with respect to x.
But we don't keep it, yes? We leave it.
For y, we don't have any x.
Yeah, okay. So then it's 2y minus nothing. Yes, just it. Just 2y.
So, and to have the derivative, to have the maximum or minimum, the critical point, we will equal this with 0, right? So we cannot find any solution for this, but we can take the second derivative or let's make the first derivative with respect to y. What is derivative with respect to y?
It would be 4 plus 2x minus 6y.
Yes. And if there is a critical point, we will equal this with 0 again, right? So let's take the df d2f dx and d2f dx dy and d2f dy squared and d2f dy dx. Okay. With respect to x, the second derivative is what?
It would be -6.
And here, with respect to y?
It would be -6.
With respect to y, just 2. This is 0, this is 0.
Yes, sorry.
2.
Just 2.
And here, with respect to y again?
It would be -6.
And here, with respect to x?
It's +2.
Yes. I show that the function has one critical point and classify the critical point. This is 4 minus 6x plus y equal to 0. This is 4 plus 2x minus xy equals to 0. This is -6, this is 2, this is -6, this is 2.
if y equals x, then we want 1 minus 2x squared plus x squared to be 0.
He is substituting here this function. This y is equal to x, and this y is equal to x. Y squared is x squared. So this is a function 1 minus 2x squared plus x squared. Okay?
So that means 1 minus x squared is 0. I've just replaced a y with an x. And that means that x is equal to plus or minus 1. So that gives us two critical points. We've got the critical point 1, 1.
You can take the x squared like in this side, so x squared equals 1. So x is positive or negative 1. What do you want to say? Speak.
Yes, I wanted to ask why he decided to choose y instead of x.
Not y instead of x. From here we have two solutions. Right? Two solutions. First solution, y equals, we have two solutions. Y equals x or y equals negative x. And he now is checking y equals x, and this is the solution. When y equals x, x is positive or negative 1. Again, two solutions. And he will put, if x equals 1, so y equals again 1. If x equals negative 1, so y equals negative 1. Because y equals x. So we have here two critical points. 1, 1, negative 1, negative 1. Okay?
Yes. Understood.
And we got the critical point minus 1, minus 1. And if you plug them into these equations, you'll see that they both work. Now, the other possibility is if y is equal to minus x.
He is checking the other solution, which is y equals negative x. He will put in the function, this function, y equals negative x. So this will be negative x squared. And this will be negative x, 2x multiply negative x, right? Instead of this y, negative x, and instead of this y, negative x. Right?
Yes.
But if y is minus x, then fx becomes 1 plus 2x squared plus x squared. So that's 1 plus 3x squared, and that's never 0.
And you know what is, from here, fx is, this is df dx. Yani the derivative of the original function with respect to x. And this is df dy. This is df dx. You wrote it f small y or f small x. This is f small x, which is the derivative of the original function with respect to x. Okay?
So that doesn't work. Y equals x works. And we found our two critical points. 1, 1, and negative 1, negative 1. Okay, but that doesn't tell us whether it's a maximum, a minimum, or a saddle point. To do that, we have to take second derivatives. So we go ahead and take the derivative of x with respect to x, and that gives us minus 2y. And the derivative of x with respect to y gives us minus 2x plus 2y. And derivative of fy with respect to y gives us 2x. And now we're going to do things separately. Once for the critical point 1, 1, and once for the critical point negative 1, minus 1. When we're at 1, 1, this is negative 2, 0, and 2.
I why he used fxx equals negative y, just this part. Can you explain?
Negative 2y?
Yes, like why he used these three f's, like xx, xy, and yy.
This is the same like d2f dx squared. And this is d2f dx dy. And this is d2f dy squared. So here we take the derivative of this with respect to x. And this is, we can take the derivative of this with respect to y here. And this, we can take the derivative of this with respect to y again.
So it's like the second derivative with the
Yes, this is the second derivative. Second derivative of 1 is 0. Second derivative of negative 2xy with respect to x is negative 2y. And this is with respect to y, with respect to x is 0, the derivative of this. And this with respect to y, again, this will be 0, this will be negative 2x. With respect to y, this will be 2y, like here.
So he used like fxy, also it's with respect to y, and the fyy, it's also with respect to y.
This with respect to y here, this one, negative 1 is 0, derivative of negative 1 is 0, derivative of negative x squared with respect to y is 0 again, with derivative of this with respect to y is just 2x. Okay? And if we take the derivative of yx, which is d2f dy dx, we take the derivative of this with respect to x. This will be 1, this will be negative 2x, and this will be 2y. And he did it, he didn't do it because they are equal. This is equal to this. He didn't do this. If xy is equal to fyx, or d2f dx dy equals to d2f dy dx. They are both the same. So he didn't do it. Okay?
Okay.
This is the second derivative, and he is substituting now this point and this point.
Okay.
And so we want our discriminant, which is AC minus B squared. So that's negative 2 times 2 minus 0 squared is negative 4. And that's negative. So this means it's a saddle point. If you
Yes, Ustaz.
Yes. B squared minus, sorry, this is AC minus B squared. What is this? Negative 2 multiply 2 minus, this is negative 4 less than 0.
If you plug in the point negative 1, the same thing happens. AC is negative 4, B squared is 0, and you get a saddle point. So the upshot is that we found two critical points, and both are saddles.
Subhanallah. Do you know what is a saddle means?
No, I don't know.
Saddle is a thing we put in the horse, on horseback. This is a saddle.
Okay, understood.
This means, I think, maximum. This means this saddle means this is maximum.
Because it's convex, yes?
Because they are less than 0, which is AC minus B squared. And this is new thing. So
no local maxima, no local minima, two saddles.
No local maximum, no local minimums, Two saddles. What does saddle means?
Okay.
Two
For our next
saddles?
problem, we're going to do
Huh?
What you just said, saddles.
Saddles.
You already said it.
where
Means
it's
like,
0 and you get a saddle.
Yes.
yeah, I mean, you already said what does it mean, saddles.
I don't know. Maybe I don't. This is first time to listen to this word in math, but
Saddle point. So the upshot is that both we found two critical points, and both are saddles. No local maxima, no local minima, two saddles.
no local maximum, no local minimum.
Okay. For our next problem, we're going to do a word problem.
طيب, let's see what does saddles mean. In mathematics, a saddle point or minimax point is a point on the surface of the graph of a function where the slopes, derivatives in orthogonal directions are all zero. A critical point, but which is not a local extremum of the function.
Okay.
Saddle, in mathematics, saddle.
Then we'll flip it.
In the last video, I talked about how if you're trying to maximize or minimize a multivariable function, you can imagine its graph. In this case, this is just a two-variable function, and we're looking at its graph. And you want to find the spots where the tangent plane is completely flat. So one way to visualize this is to imagine a flat plane that just represents a constant z value, so a constant output value for the function. And if you kind of move it up and down, you're looking for the spot where it only barely intersects with the graph at the top before it's not intersecting it with it anymore, meaning that there's no values of the function that get above that point. So you're looking just for where it's tangent, where you can find a tangent plane that's flat. But this will give you some other points, like the little local minima here, the bumps, where the value of the function at that point is higher than all of the neighbor points. You know, if you walk in any direction, you're going downhill. So that's another thing you're going to, incidentally pick up by looking for places where this tangent plane is flat. But there's also a really interesting new possibility that comes up in the context of multivariable functions. And this is the idea of a saddle point. So let me pull up another graph here. This guy. And the function that you're looking at, here I'll write it down. The function that you're looking at is f of xy is equal to x squared minus y squared. Okay? So now let's think about what the tangent plane at the origin of this entire graph would be. Now the tangent plane to this graph at the origin is actually flat. Here's what it looks like. And to convince yourself of this, let's go ahead and actually compute the partial derivatives of this function and evaluate each one at the origin. So the partial derivative with respect to x, we look here and x squared is the only spot where an x shows up, so it's 2x. And the other partial derivative, the partial with respect to y, we take the derivative of this negative y squared, and we ignore the x because it looks like a constant as far as y is concerned, and we get negative 2y. Now, if we plug in the point, the origin...
Sajida,
Yes.
if you have any question, ask me. Do you understand what he did now?
Like, I'm kind of trying to understand.
He is just speaking about a function, and he's taking the derivative of this function with respect to x one time, and the second time the derivative of this function with respect to y.
Okay, it's clear.
Into
Yes.
any one of these, we plug in the point xy is equal to 0, 0. Then what do each of these go to? Well, the top one, x equals 0, so this guy goes to 0. And similarly over here, y is 0, so this goes to 0. So both partial derivatives are 0. And what that means is if you are standing at the origin and you move in any direction, there's no slope to your movement. And one way of seeing this is to chop the graph. So if we imagine chopping it with a plane that represents a constant x value, and we kind of chop off the graph there, what you'll see, here I'll get rid of the tangent plane, what you'll see is that the curve where this intersects the graphs, so let me trace that out, the curve where it intersects the graph basically has a local maximum at that origin point. The tangent line of the curve at that point in the y direction is flat, and it's because it looks like a local maximum from that perspective. But now let's imagine chopping it in a different direction. So if instead we have the full graph, and instead of chopping it with a constant x value, we chop it with a constant y value, then in that case, we look at the curve, and if we trace out the curve where this constant y value intersects the graph, let's see what it would look like. It's also kind of this parabolic shape. Again, the tangent line is flat because it looks like a local minimum of that curve. So because it's flat in one direction and it's flat in the other direction, the tangent plane of the graph as a whole is indeed going to be flat. But notice, this is neither a local maximum nor a local minimum, because from one direction, it looked like it was a local maximum. Here, I'll get rid of that guy. It looks like it's a local maximum when you look on the curve there. But from another direction, if you chop it in another way, it looks like a local minimum. And if we look at the equations, this kind of makes sense, because if you're just thinking about movements in the x direction, the entire function looks like x squared plus some kind of constant. So the graph of that would look like an x squared parabola shape that has a local minimum. But if you're thinking of pure movements in the y direction, and you're just focused on that negative y squared component, the graph that you get for negative y squared is going to look like an upside down parabola. Here, I'll draw that again. Is going to look like an upside down parabola, and that's got a local maximum. So it's kind of like the x and y directions disagree over whether this point where you have a flat tangent plane should be a local maximum or a local minimum. And this is new to multivariable calculus. This is something that doesn't come up in single variable calculus, because when you're looking at the graph of a function, you're looking at some kind of graph, if the tangent line is 0, if the tangent line is completely flat at some point, either it's a local maximum or it's a local minimum. It can't disagree because there's only one input variable. There's only one, x as the input variable for your graph. But once we have two, it's possible that they disagree. And this kind of point has a special name. And the name is kind of after this graph that you're looking at. It's called a saddle point. Saddle point. And this is one of those rare times where I actually kind of like the terminology that mathematicians have given something, because this looks like a saddle, the sort of thing that you would put on a horse's back before riding it. So one thing that this means for us, as we're going to try to figure out ways to find the absolute maximum or the minimum of a function, as we're trying to optimize a function that might represent like profits of your company, or a cost function in a machine learning setting or something like that, is we're going to have to be able to recognize if a point is a saddle point. And if you're just looking at the graph, it's fine. You can recognize it visually. But oftentimes, if you're just given the formula of a function, it's some long thing, without looking at the graph, how would you be able to tell, just by doing certain computations to the formula, whether or not it's a saddle point? And that comes down to something called the second partial derivative test, which I will talk about in the next few videos. See you then. In the last video, I talked about how if you're trying...
Ustaz, can you send me please a video we watched just before this video?
Inshallah.
Optimization.
I'll send this for you too.
Mm-hmm.
And you have time in the evening today?
I think only like at 9 or 8 by Cairo time.
لا, I have appointment at 9. So if you want, we can start maximum at 7, from 7 to 9, or 7 to 8:50.
7, it would be 6 by my time. Okay, I can cancel actually some lessons today and study math, inshallah, I think.
طيب ان شاء الله. Let's يعني stop here and we continue at 7
Okay.
my time.